Hi, and welcome to the Assembly Lines Podcast. I'm Chris Torrance. Today we're going to do something a little bit different, and we're going to build our own Apple II emulator. So let's get started. So you might be asking yourself, why would Chris want to build his own emulator when there's dozens of perfectly good emulators that have already been developed? In fact, one of the best ones is Virtual 2 on the Mac, which supports multiple types of Apple IIs, as well as having excellent debugging tools. There's a few reasons why I wanted to build my own emulator. First, I thought it would just be a fun project to do. Second, I thought it would be a good way to relearn 6502 assembly language programming, which I've gotten a little rusty at. And finally, I've been working with Roger Wagner on his Hyperduino project. We need to rewrite the application as a web browser app, and we're thinking about using React and Typescript as the technologies. I was a little familiar with both of those, but not really comfortable enough to dive in and create a full-fledged application. I thought it would be a fun project to build an Apple II emulator while at the same time teaching myself React and Typescript. Before I forget, I wanted to go over a couple of references that'll be useful. The first one of these is the Apple II reference manual. This happens to be the one that I got as a kid, and you can see by the wear on the edges that it got a lot of use. This is really useful for looking up things like text page locations or the addresses of various subroutines. The second one is the Assembly Lines Complete Book. This is the book that Roger and I put together a few years ago based on his Soft Talk articles. The nice thing about this book is it has a complete reference section in the back, which has all of the 6502 and 65C02 instruction codes, as well as various information about them, such as which flags and registers get affected when you call them, as well as memory tables and other items. So both of these books will be really helpful when we're building our emulator. What I'm going to show today is far from being complete. In fact, it's about as bare bones as you can get, but at least it's a start for building a full-fledged emulator. Now let's dive in and see how far we've gotten. As I mentioned earlier, we're going to be using React and TypeScript as our technologies for building the emulator. React is a front-end JavaScript library that's useful for building web applications. It's easy to learn as well as being fairly responsive. I think we're going to find eventually that it's probably a little too heavyweight for actually building an emulator, but at least it'll get us up and started and we'll be able to put something up on the screen quickly. We're actually going to be doing our coding in TypeScript. TypeScript is a superset of JavaScript developed by Microsoft that adds a lot of nice features to the language, especially typing. In addition to type safety, another benefit of using TypeScript is its close integration with various development environments, such as Visual Studio Code. This will make writing the code a lot easier. Alright, let's get started. To get started quickly, we're going to use this Create React App application, which is a good way to start building a single page application. We need to make sure that we have the Node Package Manager installed on our machine and that it has a high enough version. Once we do that, then we can just use this npx command to create our React application. Alright, I've gone ahead and I've run this npx create react app application, and now I'm inside the Apple II TS directory that I created. I've already created some files in here and started coding, but let's see what's in here. You can see I have several top-level directories and files. I won't need to really mess with these unless I need to add more packages. The most important folder is the source folder, and this is where all the code lives. There's a few files in here that were created automatically, but most of these I actually created after the fact. Let's take a look at the code now. Here's the code in Visual Studio Code. I've tried to split the code into two distinct pieces, the parts that are responsible for actually displaying the emulator and the parts that are responsible for running the emulator itself. Hopefully this way it'll make it simpler in the future to change the front end in case we find that React is just too slow for our needs. The top level file is called app.tsx. This file was created automatically, but I've gone ahead and added a few things to it. The tsx file suffix indicates that it is a TypeScript file that's going to need to be compiled, and the X indicates that it contains additional React syntax for how to set up the HTML. You can see in this file that the main thing I've added is this display Apple II tag. Let's go ahead and we'll take a look at that now. Here's the display.tsx file. This is the one file that's a mix of both React display code as well as Apple II interpreter code. Let's start at the bottom and work our way up. Here at the bottom we find some React code. This is returning a div element which contains the text output as well as the Apple II processor status, just for debugging. The text output is actually the output from text page 1 in the Apple II memory. Right now this is the only thing that I actually have working. To actually run the emulator, I have a timer that's set to go off as quickly as possible. When it goes off, it calls this advance function, which then processes a single 6502 instruction and then sets a simple state flag which forces the web application to update. There's probably a more elegant way to do that, but I haven't quite figured it out yet. Since I don't have a good way yet to stop the emulator, I'm just going to have it run for about 1,000 counter iterations and then go ahead and turn off the timer. Now let's take a look at what this process instruction does. To do that, we'll dive into the file that I've called interp.ts. This just stands for interpreter. What this file is going to do is take each individual 6502 instruction, execute it, and then advance the program counter on the Apple II. And then I also have a helper function here which I've added called getTextPage1. This is just a shorthand for returning the 960 bytes that make up text page 1 from the Apple II's memory bank. There's a couple more files that we need to talk about. The actual guts of the emulator are located inside this instructions file. Let's take a look at that now. This is really the heart of the emulator. You can see at the top I have things like the processor status, the program counter. This bank 0 is the Apple II memory, so here's all 64K. To make debugging easier, I filled the entire thing with periods as an initial state. Next we have the accumulator, the X register, the Y register, and finally the stack pointer. I have a couple helper functions that I've added. I have an increment program counter, which just adds a value to the current program counter, as well as a set program counter, which just resets it to a brand new value. In addition, I have a get processor status, and this actually just returns a string which mimics the monitor's dump of the processor status when you crash to the monitor, and we'll use this for debugging. The next section are really a bunch of small functions to either get or set the various bits of the processor status. So you can see this takes care of the carry flag, the 0, interrupt, decimal, the break flag, overflow, and the negative flag. Because a lot of Apple II assembly instructions need to set various status flags, I've gone ahead and created a helper function to do that. This check status function takes a value and then sets the 0 or negative flags appropriately. I've decided to set up each 6502 instruction as a single object. The object will have the name, which for example would be like LDA for load to the accumulator. The PC is the number of bytes that this instruction takes up, and this is how far to advance the program counter once this instruction has been executed. I have a field called execute, which contains the actual code to run for that instruction. And finally, I have the addressing mode. The mode is a enum up here, which just tells which addressing mode we're using for this particular instruction. So for example, immediate, 0 page, absolute, and then some of the more obscure ones like indirect X, indirect Y, etc. And we'll see these down below when we actually define our instructions. The remainder of this file has the 6502 instructions themselves. I've actually only added about a dozen of them so far, so I have a long way to go. Here I have an array for 256 P codes. We're not actually going to need that many, but this makes it easy to index each instruction by its actual opcode. So for example, you can see here I'm defining the BCC instruction. That's opcode 0x90. BCC is the name. It advances the program counter by 2, so it takes 2 bytes. And here's the actual code. So you can see for the branch on carry clear, it says, if not is carry is set, then go ahead and do the branch. And then the last thing is this tells it that the mode is relative. So you can see here I have all the branch instructions. Here's the break instruction. Here's decrement x and y, increment x and y. And then I have a few load and store instructions. Now, one question you might be asking is, how am I actually going to get code into this? I don't have any way yet to read disks or anything like that. So at first I was just plugging in actual machine codes just to get some sort of working program going, but that quickly got tedious. So what I decided to do instead is build a simple assembler. If we look back on our display.tsx file, here I have a sample program that I've just hard-coded as a JavaScript string, and I'm just passing that into a parse assembly function. This is essentially replicating what the mini assembler does on the Apple IIe. If we look at the code within assembler.ts, it has two main chunks. The first one is to parse the entire line of code, and essentially what this is doing is breaking it up into two pieces. The first is the actual instruction name itself, so for example LDA. The second half of the line is the operand that's going to be used with that instruction, if there is one. If there is an operand, we go ahead and parse that as well, and that's up here. And essentially, this is just a whole bunch of string comparisons looking for things like number sign for immediate values, dollar signs indicating that we have a hex value, and then finally looking for some of the more interesting addressing modes such as comma x and comma y. At the end of this, what it spits out is just a whole bunch of opcodes and byte values and just returns that as an array of instructions. So going back to my display.tsx with the code, you can see I parse it, I get back an array of numbers, and then I just put this into my bank 0 memory. I decided to just throw it in at $2000, and then I set the program counter for that same value. So now that we have this code in here, we have a rudimentary emulator and assembler. Let's actually run it. To run the code, I'm going to go back to my Apple IITS directory, and I'm just going to type npm start. And this will compile the Typescript code into JavaScript, and it'll fire up a local server. Here's the web application itself. The top part is the text page 1 from the Apple II memory, and then down here is my status registers from the Apple IIe, and then finally this is just my internal counter showing where I am. So if we rerun this, you can see that my code is just filling up text page 1 with A's. And because I don't actually have that many instructions implemented yet, all I can do is really the first line of memory from 400 to 4FF. If we look in the Chrome console, we can see them actually printing out the same status registers for the Apple as well as the actual instructions themselves as they're being executed. And so you can actually go back to the beginning of the program and you can see where it started and how it's actually executing and whether there's any errors or not. If we look back at my sample assembly language program, you can see that it's really very simple. We're loading the X register with 00, we're loading the Y register with 65, and this is a decimal, and this represents a capital letter A in ASCII. Now, to be fair, this actually isn't the way the Apple II would display ASCII, but we're not going to worry about that quite yet. We store the X register actually in memory location 2008, which is actually inside of our own program right here at the end of this 0400 address. So this is actually self-modifying code.
Ooh.
Then finally we increment the X value and we check to make sure if it hasn't wrapped around to 0. Then we go back to the store X instruction to again self-modify the code, store it into the text page 1, and the loop repeats. However, you can see that we're only going to be able to execute this 256 times until we reach memory location 04FF, and then the program will just break. What we'd really like to be able to do is actually increment this 04 to go to the next lines within text page 1, and it also might be nice to increment our character that we're displaying on the screen. So I'm going to go ahead and try and add two instructions. The first is going to be an increment memory instruction so that we can actually increment this 0, 4. And then the second will be a jump so that we can jump back to the beginning of the program once we've done that increment. So let's see how we would actually add new instructions. If we go over to our instructions file, you can see we already have increment x, increment y. What I want to add is just the straight up increment memory instruction. So I'm just going to go ahead and copy this line, for example, and we'll just put it right here alphabetically, and we'll call it INC. And I'm looking in the book, and the absolute memory instruction has opcode EE, so we'll put that in here instead of E8. It is going to take 3 opcodes to do that. So 1 for the opcode itself and 2 for the memory. And now we need to actually do the code itself. So essentially what we want to do with this is we want to take the memory at bank 0 location, the high value times 256 plus the low value. And we need to actually make sure that these get passed in. Okay. And actually, just to make the code a little bit simpler, let's just pull out that value. So we're going to say V is that. Okay, once we have that value, we're going to change the memory location. So that is now equal to V plus 1. And then we're going to mod that with 256 to make sure it wraps around. Because this is JavaScript, it doesn't know anything about byte values, so this will just keep going beyond 255, which we don't want. The last thing we want to do is actually make sure to set our negative and 0 status flags. Actually, let's rather than do that, so we've got our value. Let's just change this to a variable, so let instead of constant. And then we'll increment it. Then we'll put the new value in. Then we'll check the status of it. So we don't actually have to pass V plus 1 in there. And I think that's all we need to do for our increment instruction. All right, the next instruction we wanted to do was jump, so we could jump back to the beginning of the program. So let's go ahead and we'll do that. And it doesn't really matter which of these I actually copy, but I'll just copy this one. And we'll just put this down here. So it's JMP, and the absolute jump is 4C. Okay, again, that takes up 3 bytes. We're going to pass in the low byte of the address, the high byte of the address, and now in this case we want to check the program counter and change it. So we're just going to say get rid of all of this code. Actually, we still want the V high and the V low. So I think I just want to set the program counter to be V high times 256 plus V low, and I think that might be all I need to do. Okay, there's another flavor of the jump instruction, which is the indirect jump, but we're going to save that for another day. Let's go ahead and we will try out our new instructions and see if they work. So back on the display, if we've reached 0 with our X instruction, we've wrapped all the way around. So what I want to do is I want to increment, and I want to increment memory location 2009, which should be the 04 because these are stored in low byte order first. And then I want to jump back to the beginning of the program. And in fact, actually, I can also increment the number 65 here as well. So this we're just going to have to do a little bit of math. If this is instructions 2000, this is 2001, 2002, this should be 2003. So this would change the A to a B if we're doing things correctly. And we're also, because I still don't have a great way to stop the program, let's have it run for just say 10,000 ticks. All right, now because we're running this using npm, it's actually been running the code every time we saved it. We just haven't been looking at it. So back over here, it should have been rerunning the code all the time, but let's just hit refresh just to see what happens. So there's our A's, so we haven't broken things horribly. I don't see any B's though, so something isn't quite right with our code. Is there anything in the console? Here, let me refresh this. You can see I immediately get an error, unknown instruction, inc, and jump. Okay, so it doesn't know about our new instructions, and I have a feeling I know what's wrong. One thing I forgot in the instructions is to set the actual addressing mode. Because I copied the increment x instruction, there was no addressing mode, but for inc and jump there is. So we need to have mode.absolute for increment, and we need to have the same thing for jump. And I think once I do that and save, then things might work better. So, okay, uncaught error. One good thing about using TypeScript with Chrome is it has a really nice debugger. So we can just click on these and go straight to the actual code itself. Cannot read properties of undefined. All right, there's a couple more problems which I've discovered, which I think will fix the issue. So on the increment command, when we pulled out that v variable so we can increment it, we didn't do it quite correctly. We actually did it correctly when we put it back in, but what we want to do is make sure that it doesn't go over 255. So instead of just doing the increment operator, we need to do v equals v plus 1 and then mod 256. Let's throw that down on the next line. And then we don't need to actually mod it when we put it back into bank 0. The bigger problem is with the jump instruction. So we were doing the jump correctly, setting the program counter. What we forgot was that the program counter will get immediately incremented by 3 because that's the length of the jump instruction. So we actually want to set the jump to the address -3. And I think once we do that and save it, we should be good to go. So let's go ahead and hit save. And I'll go back over to Chrome. All right, it's putting the A's in. Okay, and there it goes. Now it's actually filling in the rest of the memory. Now, right now, the way this program is written, it's just going to walk off the end of text page 1 because it doesn't know any better. So eventually I'll just start overwriting all sorts of memory and clobbering things. But since our Apple II doesn't really have any other code in it, it doesn't matter. So I think that's good enough for our Apple II interpreter for today. I hope you enjoyed this quick introduction to building an Apple II emulator. There's still a lot of work to be done. Next episode, I'll try to add some more instructions and hopefully improve the performance. If you haven't subscribed to my channel, please hit the subscribe button down below. I'd really appreciate it. Also, I have a Patreon, so if you'd like to support me that way, please look for a link in the show notes. I'll also put this code up on GitHub and I'll add a link to it down below as well. Once again, thanks for watching.